traveling miles with one spur kick, not feeling your own weight as shackles. This dream of floating light as a feather is much older than Newton's law of gravity. Thanks to airplanes, satellites, and even magnetic levitation trains, much of it is already a reality. However, none of these modes of transportation have given us true levitation because they haven't nullified gravity. Instead, they have used other forces to overpower it. So, magnetic levitation is not the same as anti-gravity. In the case of magnetic levitation, the force of gravity is counteracted by the magnetic force produced by superconducting magnets. From a scientific point of view, it is very difficult to nullify gravity. It is one of the four fundamental forces of nature, the other three being electromagnetic, weak nuclear, and strong nuclear forces. Gravity acts between masses. Mass is a measure of the amount of matter. However, mass is also responsible for the inertia of matter, that is, its resistance to changes in motion. Mass is both inertial and gravitational, and Galileo demonstrated this with his famous experiment. He dropped a wooden ball and a lead ball from the top of the Tower of Pisa, and both fell at the same speed. Although the legend says the tower was the exact location of the event, Galileo likely rolled the balls down a steep ramp. The equivalence of inertial and gravitational mass was key to Einstein's general theory of relativity, which remains very important in understanding the universe. The profound meaning of this theory is that gravity is not a real force, but a consequence of the curvature of space-time. Newton imagined gravity as a force acting at a distance, while Einstein showed that massive bodies curve space-time by their very existence. This means that nullifying gravity in one place would simultaneously nullify mass, that is, matter and space-time. This is a very high price for the pleasure of levitation. Nevertheless, in recent decades, the possibility of nullifying gravity on a local level has been seriously considered. One of the approaches is based on the fifth fundamental force. About 20 years ago, a discovery was in the spotlight of the scientific community. It was the so-called fifth force. It wasn't true anti-gravity, but a new phenomenon that seemed to surpass the strict effect of gravity. Several scientific teams of physicists and collaborators from Purdue University in the USA published results confirming the existence of this force. However, experiments did not confirm its existence at the quantum level. About 10 years ago, Russian physicist Yevgeny Polikarpov boasted of an effect he achieved with an anti-gravity device. He placed the device under a mirror equipped with a disc and magnet and measured a weight reduction of about 2%. Unfortunately, experiments at the National Institute of Standards and Technology did not confirm the existence of the fifth force. Currently, the four fundamental forces of nature are electromagnetic, weak nuclear, strong nuclear, and gravity. While the general theory of relativity describes gravity on large scales, quantum mechanics deals with behavior at the subatomic level. Is there a quantum fifth force that could explain gravity in a different way? This is a question that scientists are still investigating. Did you know that Galileo's experiment with balls can be compared to sledding down a steep hill? Regardless of the weight of the sleds, they would all slide down at the same speed. If you liked the video, like it and subscribe to the channel to help it grow and spread these smart informations.